Alright, so I just mentioned something called the Ascii Table. So the Ascii Table, or ASCII table, stands for the American Standard Code for Information Interchange. And now it sounds pretty complex. All it's saying is that every single character on your keyboard has a number correlated to it. So, for example, if we said char letter equals, let's say, capital A, like that. So when you store a value in a char, you're not really storing the value itself, more so you're storing a number. In this case, we can access that number if we say sysout, if we want to print out letter, but we're actually going to say print out the number. So this is called casting. I'll talk about that more in a bit. If we print this out, it actually printed the number 65. And if we delete this, it printed the letter A. So what's happening here is every single letter, A, B, C, D, has a corresponding ASCII value. So A is 65, B is 66, C is 67, and D is 68, so on and so forth. And these are all capital letters. That's very important. All the way up to Z, which is 90. And I'll go over these real quick. And then your lowercase numbers, or letters I mean, is 97, B is 98, C is 99, all the way up through a lowercase z, which is 122. So every single character, all your uppercase letters, your lowercase letters, punctuation, all these symbols, they all have a corresponding number, including even the spacebar. So we access those, again, by something called casting. We cast a char value as an int. So what is casting? Casting is explicit conversion. So conversion is when we take one data type and convert it to another. For example, if we have an int x equals 2, like that, we can say float y equals x, and we won't get any problems. Then we can print out y. And I'm going to comment this out for a second. And we get 2.0. So all it had to do to convert to the int as a float was just add 0.0 at the end. However, if we create another variable called int z and set that to y, now it doesn't like that, because it can't convert from a float to an int. And that's because there's a lot more to it than just adding 0.0 at the end. Now we have to take away some information, which is potentially harmful, because we can say y equals 2.5, and now we've lost some data. And that's just one more thing that's important about floats. When you initialize them like this, you have to put an f at the end to signify that it's a float and not a double. It's just something weird about Java. But here, we can't just as easily convert back from a float to an int, because there's some loss of data. So when we convert from an int to a float, this is called implicit conversion. It's also known as coercion. When we convert back, when we need to cast this float as an int, we need to explicitly tell it, hey, take whatever value you have and convert it to an int. So even if it were something like 2.9, when we convert that back to an int, like that, it actually just truncates it. So it removes everything after the decimal point, no matter how it rounds. So it always floors the number. So when we explicitly convert, this is called casting. So that's exactly what's happening up here. We're casting this char as an int. So the reason we have to cast, and it's not just coercion, is because although they are very like data types and we're not really losing too much information, or really any at all, because again, a char is just storing a number. The reason we have to cast is because Java has type checking, so it wants to make sure that you're doing that the program is doing what you want it to do. So if you pass a char in somewhere where you should be passing an int, Java's just going to let you know, hey, are you sure you want to do this? So you have to tell it, yes, I do want to take this char and turn it into a number. So that's what's happening here. So we can get rid of that. And we can actually go through and print out all of the different ASCII values. So I'm going to create a for loop. And we're going to start at 0 and go all the way up to 256. So 256 is the ceiling for the ASCII table. So we can print out I, except we're going to cast it as a char. So how we took a letter and converted it or casted it to a number, we can actually do the opposite. We can take a number and cast it to a char, so it'll print out the ASCII table equivalent. So if we print this, run this whole program, there's a lot of characters. So starting at 0, there's a lot of just this weird box with a triangle in it, and that's because the first values of the ASCII table are actually more just commands, and I think they were used for printers, actually, was how the ASCII table was developed. So it really only starts at 32. This is actually, it looks like there's nothing here, but it's actually a space bar. That's what's here. So 32 is the space, and then 33 is the exclamation point all the way up. And actually, I'm going to print out whatever value I was before we print out the character so that that's more clear. So if we scroll down, okay, so here's 32, it's the space. Then we have 33 is the exclamation point. Then we have some quotes. Up through here we got more symbols. And if you notice, something very important, the number 0, or the character for 0, is not 0, it's 48. So that's sort of evidence to suggest that if we say the char 0, that is not equal to the number 0, right? So of course it's giving me errors because it's not sure what I'm trying to say here, but I'm just going to comment it out then. So the character 0 is not the same as the number 0, because the character 0 is actually equal to the number 48, all the way up through number 9, which is 57. Then we have some more symbols, and then here we have the capital A at 65, all the way through the alphabet of capital letters. Then we have some more symbols, and then 97 is where we start the lowercase alphabet, all the way up through 122 for lowercase z. Some more symbols, and then we get a bunch of question marks, and then it actually picks up again at 161. So everything after 127. 127 is originally where the ASCII table stopped, but then there was some more data added onto it when we had more characters. So this is where we get some of the weirder characters that you might not have seen, such as that's mu, that's actually a Greek letter. And then we have upside down question mark, we have some fractions, and then a lot of characters with accents over them. We have a German letter here, so on and so forth. We have a null, or not, whatever you want to call it, a division sign. So it gets a little weird. Typically, when we're talking about the ASCII table, we're only concerned with 127 through 32. Those are really the most important characters. And even then, only some of them are important. Like, for example, this 127, this is actually the delete key. But again, it doesn't recognize that as really a character that it can print out, so it just prints out a question mark instead, because it doesn't know what to do. So that's the ASCII table. Now, how does that relate to sorting strings? Well, when we're sorting strings, we're really just comparing the ASCII values of the characters that are in the strings. So if we make an array of strings, I'm going to call it S, and we're going to put 100 strings in there. Then what we're going to do is assign 100 randomly generated strings. And the way I'm going to do that is I'm going to use a nested for loop. So I'm going to go through the string array, and then I'm going to say generate 100 different strings of length 5. So we're going to say string, we'll call this strings, just like that. String S equals, and we're going to set it to the empty string, which I've talked about before. And there's a reason we need to set it to the empty string and not just say string S, right? And I'll show you why. If we just say string S, if I say int C, we're going to call it C because it's going to represent a char, equals, and then I'm going to call the math class. So the math class is a built-in class in Java that lets you access a bunch of different mathematical functions. So ABS is the absolute value. We have max, you pass in 2 arguments and it tells you which one is higher. Min does the same thing, except the opposite. We have some constants such as e and pi, and we have trigonometric functions, everything like that. So we're actually going to call the random function, which is right here. So math.random, actually I think we want to call random int. I think that's another function that we can use. Maybe not though. Okay. Yeah, that returns a double. Okay, so we'll just say math.random. That's fine. Alright, so the way the math.random function works is this generates a number between 1 and 0. It can, or 0 and 1. It can equal 0, but it will never equal 1. So we want to generate something between 65 and 90. We're just going to make everything uppercase. So our minimum value is 65. So I'm going to say plus 65. And then here we want to multiply it by our range. So our range is 26. We have 26 letters. So now it's not liking it because this is going to return a double, so we need to, again, cast it as an int. So we're going to take this whole thing and cast that as an int. So now we've generated C from this int, and then we're going to take S, and we're going to take that letter and just attach it to the string. So S plus equals, we're going to cast C as a char. And now it doesn't like this. So this goes back to why we needed to set it to the empty string. So we never initialized it. So S is actually equal to null. And null plus something doesn't make sense. So we need to set it to the empty string, because we can say, oh, if you have an empty string, if you add on to it, that just adds letters to your string. So that's why we need to initialize it as the empty string. Now, a lot of this might be confusing, and if it is confusing to you, do not worry about it at all. I'm just doing some fancy stuff to get some random strings. Okay, so after this for loop, now we have a string, and we can say strings at I equals S, just like that. All right, and then we can print out S as well. So this should prove we have 100 randomly generated strings of length 5. So that's all that this code was doing. So this isn't the important part that I want to go over. The important part is actually doing the sorting. So I'm going to print out this just randomly generates strings of length 5. Okay, great. So after this, now we need to do the actual sorting. And again, I'm going to use a selection sort because that's what I know best. Alright, so we need to say for int I equals 0, where I is less than strings.length, and we're going to change this again to -1. Then we're going to set the min index again. So the min index is an int because the index of an array is always an int. So min index equals, we're assuming it's I, whatever we're looking at, we're going to assume is the minimum value. Then we need another array, and this is going to start at I plus 1. And it's going to go until it reaches the end of the string. Then we're going to check. So this is where we said if strings at strings at j is less than strings at min index. And now, if you notice, we can no longer do this. So it says the operator less than is undefined for the argument types java.lang.string and java.lang.string. So basically that means we can't use the less than sign to compare strings. Instead, we have to be a little bit more creative. We have to use a built-in function of the string class. So we have to say if strings at j dot compare to, and then here where it says another string, this is where we're going to put strings at min index. Okay, so now the compare to, it says type mismatch cannot convert from int to boolean. And that's because we have an if statement here. In this if statement, we need to put a boolean expression in here, so either true or false. However, this compare to function returns a number. So that number will either be positive, negative, or 0. And here's what each of those mean. So when you use the compare to function, I want you to think of subtraction. So what the compare to method is actually doing, let's say we have the word apple and the word orange. So here we're quite literally comparing apples to oranges. When we call the compare to, it looks at the first letters. So A and O. I'll zoom in a bit. So in this case, A has an ASCII value of 65. O has an ASCII value of, let me think about this. A has an ASCII value of 65, and O has an ASCII value of 79. So it starts with comparing the first two letters. So 65 is in fact less than 79. So it's going to say 65 minus 79, and we're going to get the number -14. So this is when we say apples dot compare to, I'm just going to write CT, short for compare to, oranges. And of course, since we're dealing with strings, we need to put these in quotes, like that. So apples in quotes dot compare to oranges in quotes. This gives you the number -14. So subtraction. Apples, the first letter that's different is A, so that's 65 minus, that's the compare to, and then O is 79, and we get -14, or a negative number. So when we get a negative number, that means the first word here comes first according to the ASCII table, or in other words, it comes first in the alphabet. If we said oranges.compare to apples, we'd get a positive number. If we said apples.compare to apples, we would get 0 because they're the same word. There's no difference between the strings. So those are your three options, positive, negative, and 0. The actual numbers themselves don't really matter that much. It's just whether or not it's positive, negative, or 0. So if we go back to this, if strings at j dot compare to strings at min index, if that's less than 0, right, that means whatever this phrase is minus this phrase gives you a negative number. That means this phrase comes first in the alphabet. So the min index should actually be pointing to whatever j is. So j equals the min index equals j. So if you notice, this is exactly the same thing we're doing, or that we did before with our other sort method, except this is the only line that's really different. We just need to change how we're looking at comparing these values. We can't just say which value is smaller. We actually have to say, take this string and compare it to this string, and then whatever number we get, that's going to determine how those strings relate to each other. So once we check through that, then again, we need to do the swapping. So before we used an int because we were dealing with an array of ints. Here we have an array of strings. So we need to say string temp equals strings at I equals strings at min index, and strings at min index equals temp. So it's sort of a flow. There's a flow to it. So you start with temp, you say temp equals I equals min equals temp. So whatever goes here, you bring that down on the next line. Then whatever goes here, you bring that down on the next line. And then whatever's here, you would have brought it down, but that's already up here, so we're done with that. But that's the way you can think about the swap. Okay, so now that we've swapped it, we should be able to print out all of the values. Sys out strings at I. And if we print it out, first before I do that, I want to print out an extra line separating the sorted from the unsorted. Okay, so these are all our randomly generated strings. So we look through, everything looks great. Then we go down, and then here, everything is alphabetized. So it starts with Arnmer, and then Batuk. Everything is in alphabetical order. Now, you might also be wondering about the Compareto method. When we compared apple and orange, the first letter was different. But what if we were comparing apple to something like ankle? Right? So the A and the A are the same letter. So theoretically you would get 0. But if these two are the same letter, it actually goes to the next letter and compares these. So in this case, N comes first in the alphabet relative to P. So that means ankle. If we said ankle dot compare to apple, we would get a negative number. Or if we said apple dot compare to ankle, we'd get a positive number. That's because ankle comes first in the alphabet. Now, another thing that's important to keep in mind. We said that a capital A has the ASCII value 65, and a lowercase a has the ASCII value of a 97. So when we compare apple to something like ankle, with a lowercase a, apple would come first, even though we just determined that ankle comes first when we compared it over here. And that's because A has a 97, so it's already assuming that this letter right here comes way later in the alphabet. So even if we compared a capital zebra with a lowercase apple or ankle, whatever you want to say, it would say that zebra comes first, even though Z is the last letter and A is the first letter in the alphabet. So you want to make sure that when you're comparing strings, unless you want to separate, put the capital letters first, then put all the lowercase words, or capital words first, then the lowercase words after. If you actually want to alphabetize regardless if it's capital or lowercase, then this is something you need to keep in mind, because there's different values for whether or not it's capital or lowercase.